Yeah, started the recording. Okay, so we're here. I am more than likely going to end early today for several reasons. First of all, there's a lot of construction going outside my home right now, and I can't really hear that much of what's going on. Second reason is my internet's been spotty the last couple of days, so I'm afraid we're going to stop at any moment. And the third reason is I want you to have time to do the quiz. So for those reasons, I'll probably end fairly early today. So turn down, okay? So here we are, 7.2. I'll try to finish off 7.2. If I have a chance, I'll sneak in some of 7.3, at least the introductory part. Okay, and homework-wise, we are up to here, right? So I just had one more problem to show you in 7.2, but it's a long one. So we'll do that and then introduce some of 7.3. All right, so here we go for the quiz. So be ready for those of you that are with me right now. You can take a screenshot or get it on your cell phone or just look at the video later. All right, so number one, use integration by parts to evaluate the integral of x cubed e to the x dx. Okay, I'll go ahead and give you some hints. We mentioned this before, that you'll have to integrate by parts 3 times. If you do it the right way, the first time you do it, you'll get it down to x squared e to the x. Do it one more time, you'll get x e to the x. Do it one more time, you just have e to the x. Okay, that's not all you'll have some other stuff also, but here's one where you have to have an I1 and an I2 and an I3 and so forth. So my advice is to look back at what we did when we had to integrate by parts twice. Okay, and I alluded to that fact that, you know, if you had x to the 10th, then you'd have to go x to the 9th, 8th, 7th, and I said, I'll never make you do that much, but I might make you go up to x cubed. So here I am, I'm making you do something with x cubed e to the x. Okay, number 2, integral from 0 to pi over 2 of sine x to the 4th power dx. My computer typed it out as that, but it's the same thing as this, sine to the 4th x dx. Now, we did a cosine to the 4th. So look in your notes how we did a cosine to the 4th, and it's very similar to work out the sine to the 4th. There's a formula for a sine squared, right? Sine squared of theta is 1 minus cosine 2 theta over 2. Remember that one? Okay, so that's what we have. Due 11:59 p.m. tonight, Friday. Open book, open note, open discussion. You can talk about it all you want, but I just, as it's in your own writing, obviously, you should write it up yourself. You get some other people to help you. Okay, so my hints are, you have to integrate this by parts 3 times. Okay. And the first time you get it down to x squared, it's not only x squared, there's going to be some other stuff with it. And the next time you get x with e to the x, and not only that, but there's some other stuff. And then you have to do it again to just get e to the x. Okay, and integrate sine to the 4th. Look at what we did for cosine to the 4th and do something similar. Okay, so that is the quiz due 11:59 p.m. tonight for everybody. Okay, so just email me as usual. All right, and now I'm going to go back and do problem 31, tangent to the 5th. Okay, this is probably the longest one that you're going to do from this set. So how do I integrate tangent to the 5th in 7.2? Okay, so first I break it down into tangent cubed and tangent squared. Okay, just to let you know, it's very noisy here. So if you try to unmute yourself and say something, I won't be able to hear you. So if you have a question, put it in the chat. It's so noisy outside that I just can't hear you. I can barely hear myself right now, but anyway. Tangent cubed, tangent squared. Now tangent squared, we know, is secant squared minus 1. All right, then I distribute. So multiply this out. So I break this up into tangent cubed, secant squared, minus a tangent cubed. Okay, so I have to take a time out and figure out I1, and another time out to figure out I2. So the original I is now I1 minus I2. Fortunately, this one looks like stuff with tangent followed by secant squared, right? One of the rules from last time. So for I1, let u be tangent x, whose derivative is secant squared x. That gives me integral of u cubed. So integral of u cubed du is u to the 4th over 4 plus c1. And the reason why I put plus C1 is we've got so many integrals floating around here. You can't just call them all C because that implies they all have to be the same, but they don't have to be the same. So I'm going to use C1, C2, right, C3. But at the very final answer, you have a C1 and a C2 and a C3 and C4. We put them all together, then you can just say plus C. All right, so that becomes u to the fourth over 4. So 1/4 tangent to the fourth x plus C1. So that's my I1. Okay, so this one turns out to be this, which by the way is very easy to check. What's the derivative of this? Well, 4 knocks out to 1/4, you have tangent cubed, and then by the chain rule times the derivative of tangent, which is secant squared. So it works. Okay, now how do I do I2? Tangent cubed. Why work it out just like the other one? Break it into a tangent times tangent squared. Okay, and then change tangent squared to secant squared minus 1 once again. And then I distribute. And yes, I'm breaking up the integral. The integral of a difference is a difference of the integrals. You're allowed to split it into two. So this gives me integral of tangent x secant squared x, which I'm now calling I3, minus the integral of tangent x, which is I4. So this is all I2. So I2 is I3 minus I4. So again, I have to take a timeout. Again, this is sort of a recursion theme for you computer science people, where you call a sub-program, and that sub-program works something out, then brings it back, and then something else brings something back, and you eventually work your way back up to the original called program, so to speak. So I2 is I3 minus I4. So u equals tangent x, du is secant squared x dx. So I3 is the integral of u du, which is u squared over 2 plus c2. So 1/2 tangent squared x plus c2. That's my I3. And by the way, again, that's easy to double check. What's the derivative of this? We already know the derivative of any constant is 0. So 2 knocks out the half, you get tangent x. Then by the chain root times the root of tangent x, which again is secant squared x. So that works. And then I4, integral of tangent x. Okay. Well, that was one of the new ones that we learned. ln absolute value of secant x plus c3. All right, put the integral of the tangent. Again, put this on your next cheat sheet. I think it helps you. Bottom of page 482, integral of tangent, ln absolute secant x plus c. Okay, so now I2 was I3 minus I4. So this is where you work your way back up to the original integral. Okay, so I3 was this stuff, right? 1/2 tangent squared x plus c2, 1/2 tangent squared x minus I4, so minus ln absolute value of secant x. And then the C3 and C4, sorry, the C2 and C3, I'm combining it to just C4 now. Okay, so I have 1/2 tangent squared x minus ln absolute secant x. This is okay, but I like it better with a positive and a cosine. Okay, and you might say, do I have to do this step? No, you don't have to, but you know, to me, why have a negative and a secant when you can have a positive and a cosine? So I'm switching to 1/2 tangent squared x plus ln absolute cosine x plus c4. That's my I2. And finally, I can go back to the original I, which is I1 minus I2. So the original I1, 1/4 tangent to the fourth x minus I2. So I subtract all this stuff, which means that's a minus, that's a minus. So 1/4 tangent to the fourth x minus 1/2 tangent squared x minus ln absolute value of cosine x. And then the C1, C2, C3 all combined, I can now finally say is just plus C. And there we go. Okay. All right, so that is the end of 7.2. I'm now officially knocking off this. So technically, if I stop right now, I'd just be on par, but I'm not going to stop now. I'll go a little bit ahead, and we'll still probably end early. Then hopefully you can start working on the quiz. Okay, so up to 7.3. Okay, so 7.3 is on trig substitutions. Introduction to that. It sounds the same thing as section 2, but it isn't. Trig substitution. In fact, if you look at the problems, you hardly see any trig at all. So 7.3, the assignment was 1, 2, and 3 to 29. Okay, so let me go ahead and show that to you, page 491. Okay. The original integrals do not start off with any trig. Right, so you notice these problems, there's no trig anywhere. You end up introducing a trig to work the problems out. Okay, so there we are. There's a table on the bottom of 486. This one here. You'll want to put this on your next cheat sheet. Okay. I'll give you, you really want to condense it and not put everything down. You can probably survive with just this right here. Okay. You don't really need this. I mean, it's correct. We're just saying theta is a quote unquote nice angle. And here are the identities involved. Okay. So you can survive with just putting this on your cheat sheet. And I'm going to try to show you one example of each today. These are the identities involved, but you've already written them down somewhere, right? 1 plus tangent squared, secant squared, which means tangent squared is secant squared minus 1. And we already know this is a variety of cosine squared plus sine squared equals 1, right? 1 minus sine squared equals cosine squared. We already know 1 plus tangent squared is secant squared. Subtract 1 on both sides, and you get this one over here. Okay, so these are trig substitutions. So for the problems in this section, you'll look for the appropriate type. By the way, if we were even meeting face to face, I still would not have you memorize this. I would let you have this on your cheat sheet. Okay, by making use of these substitutions, you can make the problem a lot easier. Okay, let me check something in the chat. Okay, get this away. Okay, I've already put the quiz away. I can't get it now. Maybe at the end. It's on the video. Okay, so you can always look at the video also. Okay, so 7.3. Quick review of right triangle trigonometry. You might recall SOHCAHTOA. So if you have a right triangle, here's theta. This is considered the opposite side, OPP. This is the hypotenuse, HYP. This is the adjacent side, ADJ. Right? And a reminder, for adjacent, you might say, well, there's two sides that are adjacent. Yes, but one of them already has a name, the hypotenuse. Right? So the adjacent side is the one that is not the hypotenuse. Right? So if you're given an angle opposite, you might say there's two adjacents, yeah, but one of them is already called hypotenuse. Okay, so adjacent. And then you might recall we have our SOHCAHTOA. You might recall SOHCAHTOA. And what is SOHCAHTOA? Sine is opposite over hypotenuse. So the sine of theta is the opposite divided by the hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent of theta is opposite over the adjacent, right? Okay. All right, so I was going to show you 1, 2, and 3, hopefully, which illustrates each of these types. Okay, now 1, 2, and 3, they already give you the hint, but suppose they don't give you the hint. Okay, integral dx over x squared, radical 4 minus x squared. Okay, there's a radical 4 minus x squared. 4 minus x squared, that's like the first one. A squared minus x squared. So if this is 4, that means a is 2. So my substitution is going to be x equals 2 sine theta. So that's the first one. Okay. See, if you look at this, say, I don't know how to integrate that. The whole idea is to change it into a trig integral so that there's no more square root. So let x equals 2 sine theta, differentiate both sides. Dx is equal to 2 cosine theta d theta. Then I substitute. Okay, so right here is my dx. I put 2 cosine theta d theta. So that becomes that. X squared is this thing squared, 4 sine squared theta. 4 minus x squared. So 4 minus 4 sine squared theta. And believe it or not, this turns out to get rid of the square root. You end up with a trig integral. Okay, factor out the 4. 1 minus sine squared. And what is 1 minus sine squared? Cosine squared. And what's the square root of all this? 2 cosine theta, which is nice. That's what I want. Provided theta was in the angle that it says, you normally don't have to worry about it. Just assume that it's good. So we don't have to worry about plus or minus. Just change it to 2 cosine theta. And 2 cosine theta cancels that. I got a 4 in the bottom, take it out as 1/4. And I have a sine squared in the bottom, which means cosecant squared on top. The reciprocal of the sine is a cosecant. Okay, and what's the integral of cosecant squared? Negative cotangent. So I have negative 1/4 cotangent theta plus c. Okay, so it ends up being a fairly nice integral. However, we're not done. In fact, we're far from done. Calculus is done. We now have to switch over to trig. Okay, so one more time, I have the square root of 4 minus x squared on page 486. That's that first square root there. X equals a sine theta, right? A squared was 4, therefore a is 2. Substitute. So dx, I write this stuff. X, I put this stuff. If you do it the right way, the square root comes out nice. Then you do the integral. Okay. I have this, but I'm not done. I mean, stop and think about it. You can't leave your answer like that, right? What was the original problem? The original problem was x. So you can't leave your answer as theta. So how do I switch back? I switch over to trig now. So trig, x is 2 sine theta divided by 2. Sine of theta is x over 2. So I draw myself a triangle. Sine is what divided by what? Opposite over hypotenuse. So from here, I did x divided by 2, opposite over hypotenuse. And then do your Pythagorean theorem, a squared plus b squared equals c squared, to find the adjacent side. You can work it out. It comes out to be square root of 4 minus x squared. There is a nice little trade secret. Quite often, this turns out to be something from the original. In other words, if I look back at the original and see, oh, square root of 4 minus x squared, okay, you have more than 50-50 chance that this is going to be square root of 4 minus x squared. Now, you should double check that that's correct, but it is. But you stop and think about it as the original problem. If I had this, it would not be strange. It would not be unusual for my answer to have a square root of 4 minus x squared, right? So that kind of figures into the game plan. I mean, it would be highly unusual for me to have this to be square root of 9 minus x squared in the answer, right? But it's very logical that somewhere in the answer, there might be a square root of 4 minus x squared. Okay. So again, the trade secret is from here. I've seen enough of these to know what to do right away. I could do my a squared plus b squared equals c squared, but I'll just give you the trade secret. If you just look at the funny square root, that's probably going to be it. Square root of 4 minus x squared. Let's double check. Okay. Is it true that the Pythagorean theorem holds? What do you get when you square this? Well, when you square this, you get 4 minus x squared. What do you get when you square that? X squared. Add them up, you get 4, which is 2 squared. So indeed, a squared plus b squared is equal to c squared. So it's nice to double check yourself that this works. All right, so I want my integral is negative 1/4 cotangent. Oh boy, what is cotangent? Cotangent is the reciprocal of the tangent, right? So tangent, TOA, was opposite over adjacent. So cotangent is adjacent over the opposite. So I leave that negative 1/4 alone. And I want adjacent over the opposite. So radical 4 minus x squared over x. And a little bit of touch up. So negative square root of 4 minus x squared over 4x plus c, final answer. Okay, so that's how I figured out cotangent. Cotangent is adjacent over opposite because tangent is opposite over adjacent, right? And there we go. So this is my final answer that I have right here. Okay, how do you know what the angle is in the drawing you drew? Well, you can set it arbitrarily. You can make any triangle that you wish. I always like to draw this triangle, but it doesn't really matter. I mean, you can always rotate it, turn it like that, and like that. But just set any angle as theta. I mean, I could let that one be theta. It wouldn't change the problem significantly. It's equivalent to saying just turn the picture or whatever. Okay, so anyway, this is my final answer. All right, and I'll try to show you a couple more. Okay, an interesting side note is that means if you do it the right way, what's the derivative of this supposed to be? It's supposed to be that. I'll let you work that out. But one side note also, if you try to take the derivative of this in Calc 1, you get this. There's no trig involved, right? Think back to Calc 1. If I ask, what's the derivative of this? It's kind of clumsy, looks like quotient rule, blah, 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 blah. It'll come up with this. There's no trig involved. But when you go backwards, you have to introduce all this trig, right? So no trig. Then all of a sudden you sneak in all this trig all over the place. And then the final answer, there's no more trig. So the trig is just a tool to help you get all this stuff. But, you know, ultimately there's no trig in your final answer. And yes, if you were to actually differentiate, there wouldn't be any trig at all, right? If I say, give me the derivative of that, you don't see any sine or cosine or cotangent or whatever. It's all here. But going backwards, interesting enough, I mean, we saw a whole bunch of stuff. We saw cosine, sine, cosecant, cotangent. We had 4 trig functions showing up. And then the final answer doesn't have any at all. Okay. All right, I'll show you a couple more. Number 2. So number 2 was a sign, it's even, which means you don't have the answer in the back of the book. No worries, I'll show it to you. Okay, integral of x cubed over radical x squared plus 4. So x squared plus 4. Radical a squared plus x squared, which is the same as x squared plus a squared. So it's the second one. So then a is 2. So x equals a tangent theta. It looks like this one. So I'm going to say x is 2 tangent theta. Okay, what's the derivative of 2 tangent theta? 2 secant squared theta d theta. Okay, so x is 2 tan theta, dx is 2 secant squared theta d theta. Now I substitute dx, and by the way, when you write dx like that, it's like it's on top. Dx is like dx over 1. So in place of dx, I write all this stuff. See, this is my dx, 2 secant squared theta d theta. X cubed, I cube that, 8 tangent cubed theta. 2 tan theta cubed is that, that's my x cubed. And square root of x squared plus 4. So x squared is 4 tangent squared theta plus 4. That's my x squared. And now notice here, you can factor out a 4. 4 times tangent squared theta plus 1. And what is tangent squared theta plus 1? Secant squared. So I have the square root of 4 secant squared theta. That's just 2 secant theta. So that's nice. So by making this manipulation, I'm able to get rid of the square roots. Okay, and I notice the 2's cancel out. I can cancel one of those secants out. Let's see, this was secant squared, right? That's secant. So I'm going to be left with 8, which I bring out, tangent cubed, secant theta, d theta. And now this is a trig integral. So we had a variety that had secant squared. This doesn't have a secant squared, right? If I have stuff with tangent theta, then the derivative has secant squared theta d theta. I don't have a secant squared. So the other option is a secant theta tangent theta. Is there a secant theta tangent theta here? Yes, there is. Which means I want stuff with secant theta times secant theta tangent theta. Okay, so the question is, can I write this tangent squared so that it only says secant? Sure. Tangent squared is equal to secant squared minus 1. So now this looks like stuff with secant theta times secant theta, tangent theta, d theta. So I substitute u equals secant theta, du equals secant theta, tangent theta, d theta. So all of this is my du, and here's my u. So when I integrate, I've got 8 integral of u squared minus 1. All right, u cubed over 3 minus u plus c. Change u back to what it was, secant. So I have 1/3 secant cubed theta minus secant theta plus c. Right here. Okay, calculus is over, trig starts. You can't leave your answer as that. It doesn't make sense, right? Look at the original. The original had x. So if the original has x, you can't leave your answer with theta. So I have to switch back to the original. How do we do that? With trig now. Okay, so is there a relationship between x and theta? Yes, way back here. X is 2 tan theta. Divide both sides by 2. Tangent of theta is x over 2. Okay, so I draw myself a triangle. Again, I think this hopefully answers your question. You can draw the triangle any way you want, as long as you have a right triangle. I decided to call this one theta. If you want to call this one theta, it's the same thing, because if you just turn the picture, it is just like mine, or do a reflection. Okay, so just draw any right triangle, call one of the leftover angles theta. Okay, tangent, TOA, again, is opposite over adjacent. So opposite over adjacent is x over 2. Opposite, adjacent. Okay, and now I have to figure out the hypotenuse. Option 1, a squared plus b squared equals c squared. Option 2, just peek back at the original and it's probably right. Square root of x squared plus 4. I'm just going to put it. It's almost always right for these kind of problems. But double check. Is it true that a squared plus b squared equals c squared? Okay, so what is this thing squared? X squared. What is this thing squared? 4. Add them up. X squared plus 4, which is equal to the square of this. So it definitely works. Right, so now for the answer, 8 times 1/3 secant cubed minus secant plus c. Okay, and now secant. Oh boy, secant is the reciprocal of the cosine. Cosine ka is adjacent over hypotenuse. Therefore, secant is hypotenuse over adjacent. So right here, hypotenuse over adjacent. Radical x squared plus 4 over 2. Radical x squared plus 4 over 2. And there we go. So there's my final answer. And you could leave it like that. You could do more, but I don't feel like it. Bottom line, the derivative of this stuff, if you do it the right way, is this. But if you were to take the derivative of this, there's no trig. But when you go the other way, so you can see integration is a lot harder than differentiation. We introduce all this trig, right? So look at the original, no trig. So in the process of doing this, I got trig, 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 all this trig, right triangle trig, and then the final answer, the trig disappears. Interestingly enough. Okay. All right, then I was going to show you number 3, which showed you the last type. So my goal for today was to show you exactly one of each of these. Okay, and then so next time you would at least seen one of each. Okay, number 3, radical x squared minus 4 over x. So square root of x squared minus a squared. X squared minus a squared. X is a secant theta, it says. Okay. And again, in this case, a is 2. It's x squared minus 4, right? So x is 2 secant theta. Dx is 2 secant theta, tangent theta, d theta. The derivative of secant is secant tangent. And we're using this Leibniz notation. using the d's. Okay, we could have said in Calc 1, right, dx d theta equals 2 secant theta tan theta. Then pretend you multiply both sides by d theta, and it looks like this. Okay, so right here, I'm putting 2 secant theta tangent theta d theta. And radical x squared minus 4, x squared is 4 secant squared, right? I'm squaring this. So 4 secant squared theta minus 4. And the bottom is 2 secant theta. And very conveniently, that the 2 secant theta cancels that 2 secant theta. Factor out the 4. Secant squared minus 1. And what is secant squared minus 1? Tangent squared. Okay, 2's cancel, secant theta cancels. I got a tangent here. I'm left with the square root of 4 tangent squared. And what's the square root of 4 tangent squared? 2 tan theta. Okay, take out the 2. Tangent times tangent, tangent squared. Integrate tangent squared. We saw that earlier. Make it secant squared minus 1. And there we go. All right, so integral of secant squared is tangent. Integral of -1 is negative theta plus c. So 2 times parentheses tan theta minus theta plus c. Okay, and again, calculus is done now for trig. You can't leave your answer like theta, right? You got to have it in terms of x. So what's the relationship between theta and x? I know x is 2 secant theta. So x is 2 secant theta, divide both sides by 2. Secant theta is x over 2. Okay. Now, I don't like secant. I'm guessing you probably don't like secant either. So let's take the reciprocal. The reciprocal of the secant is the cosine. So cosine is the flip of this, 2 over x. Which incidentally means theta is inverse cosine of 2 over x. I'm going to need that right over there. Right, so I'm going to put that right over here. All right, so theta, draw my triangle. Again, I always draw this, but you can make the triangle look like that or like that, and you can put the theta over there. It would be the same thing. It's just like mine, tilted, you know, that way, or maybe a reflection or whatever. Okay, cosine. Cosine is adjacent over hypotenuse. So I lay down the adjacent as 2, hypotenuse is x. For this side, you can do a squared plus b squared equals c squared, or it's probably the square root from the original, radical x squared minus 4. I'm just putting it down, radical x squared minus 4. And then double check. What is this thing squared? X squared minus 4. What is this squared? 4. Add them up, the 4's cancel out. You have x squared, which is the hypotenuse squared. So it definitely works. All right, so now I'm ready to plug back into my integral. Where did it go, my integral? It's right here, right? So 2 times tangent theta. Tangent is opposite over adjacent. So radical x squared minus 4 divided by 2 minus theta, which is arc cosine 2 over x plus c. That's a minus sign there. Okay, you can leave it like that, or alternatively, you can decide to distribute the 2 because I noticed the 2's cancel out. So good final answer is radical x squared minus 4 minus 2 arc cosine or inverse cosine of 2 over x plus c. Okay, so this was an introduction to how trig substitutions are going to work. And I've shown you literally one of each type, problems 1, 2, and 3. So problem 1 looked like that. Problem 2 looked like that. Problem 3 looked like that. But I wanted to stop here right now so you can work on the quiz if you wish, okay? So I'll show you the quiz one more time. Okay, so if you didn't get it already, do a screenshot or take a picture on your cell phone or just watch the video later. Okay, so you have until 11:59 tonight. Integrate by parts 3 times. 1 time gets it down to x squared, e to the x, and some other stuff. I mean, it's not that easy, of course. It's just not just x squared. Do it again, you get x e to the x. Do it again, you have just e to the x. You have to integrate by parts 3 times. This one is the same as this, integral of sine to the fourth. Look at how we did cosine to the fourth, and it's going to be very similar. Okay. All right, so that is that. Let me stop the share. Check to see if there's anything in the chat. And if not, I'll let you loose so you can get started on the quiz. Yeah. Okay, I think I've caught up with the chat. So anybody with a question? Otherwise, I'll let you go work on the quiz, and that'll do it for today. All right, so have a good weekend. Quiz due 11:59 tonight, and we'll see you next time. Okay. All right, bye, everybody.
All right, take care, Professor.
Thank you, Professor.